Can you guys hear me? Okay. Hello, everybody. This is Team Forest Projects. Our title is Breast Cancer or Not, and our team members are me, Jeremiah Chun. If the other
Evan Lee.
William Park.
David Kim.
and David Park. I don't think he's here today, but yes, he's our other member. So here's a brief table of contents for our project. So our data science project, it revolves around the topic of breast cancer, and breast cancer occurs when cells in the breast grow and spread uncontrollably, just like other types of cancer. And in order to cure breast cancer, you first have to identify what type of cancer is present for a patient. So to sum it up, basically there's two types of tumors. Benign is normal and usually not dangerous and has more smooth and regular borders, while malignant tumors are abnormal and they have a more abstract shape, needing instant medical attention. From this, our project's objective is to find whether a patient has a normal, benign, or abnormal malignant tumor. And since malignant tumors have more irregular borders, our hypothesis is that the shape of the lump will primarily determine whether a tumor is abnormal or normal. So breast cancer is a prominent and universal problem, and is especially threatening for women, being estimated that 1 out of every 3 women in the United States will get breast cancer in their lifetime. So first, identifying this cancer is essential because it will save doctors and other medical professionals time. In the medical field, where every second counts, finding the type of tumor present can save lives. So for our project, we chose a data set from Kaggle. This data set consists of various factors such as radius of the tumor or smoothness of the skin that can help detect what type of tumor is present. And this data set is realistic. It's not simulated, as this data is taken from diagnostic x-rays, with each data point being distinct. So, oh, I was on the wrong slide, but here's our method used. We used classification and machine learning to see the distribution of different variables and see the most important factors of a tumor. So starting off with data exploration, we were able to first clean up the data, which includes removing null values, removing unnecessary columns, and removing outliers. After that, we were able to see the distribution of numerous variables in the form of histograms. We found from this that most variables have a normal distribution, being symmetric around the mean and having a typical standard deviation. There were some exceptions, however, with some variables such as area, which, as you can see right here, is skewed to the right. Next, we found the distribution of normal and abnormal tumors. As you can see in the graphs, the blue represents the benign or normal tumors, while the orange represents the malignant or abnormal tumors. And from this, we observed that the abnormal tumors in general covered larger measurements than normal tumors, while having a greater range. So like, for example, abnormal tumors had a greater area, greater radii, greater texture, and greater perimeters than normal tumors in general. And for example, for range, if you could see on the top right, you could see concavity, and then you could see that the abnormal tumor, it ranges from 0.02 to 0.38, while the normal tumor only ranges from 0 to 0.1-ish. Next, we found the densities of the different variables. So to do this, we had to convert string variables such as like diagnosis. The diagnosis column will tell us whether a patient had malignant or benign cancers. We had to convert those into numeric values to do mathematical functions to them. And then from this, we can see where the most frequent value of each variable is based on the bell curve, which accounts for frequency and measurements. We also found correlations between different variables using linear regression, where we saw that the strongest 2 correlations were between concavity and compactness, which had a R value of 0.88 for concavity and concave points. I'm sorry, for concavity and compactness, while concavity and concave points that had a R value of 0.92. So testing our correlations with separate variables using the line graphs from the previous slide, that can be inefficient. So in order to refine this process, we instead used a correlation matrix because it's an efficient and straightforward method to visualize the strongest correlations. And the strongest correlations, just like the previous slide, were between concavity slash compactness and concavity slash concave points. There are other stronger correlations, such as area and perimeter, which I believe had a correlation of 0.99, but those are expected to be in stronger correlation because of their mathematical nature. Because, for example, area is based around perimeter. They have the same variables, so it's expected to have a very strong correlation. So we didn't use those variables when it came to classifying a patient between malignant and benign tumors. And in addition to the mathematical nature, they're also just not relevant or useful to the overall scope. For example, the correlation between area and perimeter is not going to help us really that much in determining whether a person will have malignant or benign tumor. So from those graphs, we concluded that the variables with the highest correlation will have the highest importance in finding out what type of tumor is present in a patient. And using logistic regression, we were able to find those coefficients, or the importance of each variable in the overall equation of our target variable. So essentially, logistic regression, there are just like, it's kind of like y equals mx plus b, where like x is, but there's going to be multiple variables that classify whether a person has malignant or benign tumor. So x in a like slope intercept equation, that kind of represents each separate variable, and the coefficient, so that like m in y equals mx plus b, that kind of represents the importance, because the higher the slope is, just like in a graph, the higher number m is, the higher the slope. Kind of the same concept. The higher coefficient that variable has, the more important it is in considering whether, in our case, whether someone has a malignant or benign tumor. So, and this relates to the other slides, because we found out that the more correlations that they have with each other, each variable, the higher importance it's going to have, which will be more helpful to finding whether a person has a normal or abnormal tumor. And for the graphs, you can see, so the y-axis is the diagnosis. So basically 0 is the normal or benign tumor, while 1 is the abnormal tumor. And you could see this curve, which kind of represents like the boundary or the zone where each where the cutoff is, whether someone has a benign or malignant tumor. And we use the two variables with the strongest importance, in this case concavity and concave points. So we experimented with machine learning algorithms, and we used these different algorithms to see which model could best predict what type of breast cancer a patient has. So essentially, we use 3 types of models. We use KNN, SVM, so K nearest neighbors, support vector machines, and then decision tree accordingly. So we tested, we scaled, and then we trained the most important variables that we found from the logistic regression, and we were able to see the different accuracies and visualizations that each model had. As you can see in these 2 graphs, decision tree, we couldn't find a way to graph it, so that's just the hierarchy of it. And you're basically able to see the accuracies that each model had, and the higher the accuracy, the better the model was at predicting whether a person had a benign or malignant tumor. And as you can see, the different colors represent, so blue is benign, orange is malignant. And you could see in these 2 cases, around the approximate boundary in which these 2 variables were cut off. So from all these data analysis results, we found that concavity, or the curvature of the lump of the tumor, was the most important factor in determining whether a tumor was normal or abnormal. And this supports our hypothesis, since we originally stated that shape would affect whether someone had a normal or abnormal tumor, and concavity is determined by shape. So from this, we used the support vector machine learning algorithm, since that was the most accurate out of the 3, which I believe it was like 94%-ish. So yeah, we use the support vector machine, and this makes sense because SVM is perfect for binary classification, and it's able to create a boundary between the 2 distinct groups of data points, in which our case, it was the normal and abnormal tumors. So support vector machine, it's reasonable that it was the most accurate out of the 3 machine learning algorithms. And we hope that this data science project can further help breast cancer analysis. These were our 2 references. This was a reference of the information about breast cancer, and this was our data set from Kaggle. And thank you.
Okay, thank you. Yep, so questions and comments?
I just have like a quick question. Can you go back to like the one, like the curve one, to figure out which variables were the strongest? Yeah, this one.
This one, yes.
Yeah, I was just wondering, can you re-explain what the 2 right side graphs do again?
Oh yeah, so So again, so these were the two strongest points according to our logistic regression. As you can see, concavity and concave points, which have these relatable importances. And basically for the diagnosis, so basically these are the two variables, right? And then we're comparing them to see, because basically what logistic regression is, it uses probability to determine the state in which someone has a normal or abnormal tumor. And how you can find that is basically in the diagnosis axis, 0 is benign or normal, and then you could see 1 is malignant or abnormal. So these data points kind of show, like, because as you can see, the data points are either 0 or 1. There's no in between, because logistic regression uses discrete variables. So basically, it's these graphs show like the kind of tendency in which the two groups are kind of separated, if that makes sense.
Yeah, got it. Thank you. I think I just like misread the axis or something.
Oh, okay, of course.
Okay. So any other questions? So I have one question. So you're using the advanced the machine learning algorithms.
Yes.
So yeah, I just want to ask some non-technical questions. So
Yeah.
in team, and then what is individual contributions?
The
sharing or maybe a couple of
yeah. So yeah, so for example, these machine learning algorithms, this was primarily me because I had experience with machine learning before. So I utilized these in terms of like such as like these distribution features, etc. I believe like William and the two Davids as well as Evan, they worked on it, and they also worked on the research of breast cancer as well as identifying our problem.
So in the middle, and you changed the topic, right?
Yes, we did. We had many potential ideas, but we ended up.
in a relatively in a short time, and
Yeah.
then actually you did in
Yes.
a lot of things.
Yeah. We changed. I believe we changed. I believe last Saturday, we changed to breast cancer officially. Might have been. Yeah, it was Saturday. So yeah, it was extremely a lot of work, but it was kind of short because like this data set was relatively like easy to do because there's so many like different kinds of variables. So it was kind of easy like analyzing like the relationships.
So anybody has some the background knowledge in this the topic or biology and medical kind of science?
I don't think anyone has.
How did you select this topic?
Yeah, so we were looking for data sets that best like fulfilled the idea of data science, and actually kind of know like some field of this because my grandma actually she has Alzheimer's, and like so, and she had like these type of problems, so it was kind of like relatable to me, at least. I'm not sure for my other team members, but yeah.
Okay. All right. So any other questions?
I have a quick question.
Yeah.
Since you use a lot of like machine learning algorithms, the
Yeah.
data is really important. So
Mhm.
for the data, were there any like missing values or like unusable parts of the data that
Yes.
existed in the data?
Yeah. There were some columns or some rows that had missing data values, but we removed them. But since there's already so many values in the data set itself, it's not really going to impact the different distribution of different groups. And then in terms of columns, yes, there were some columns that we had to remove because they were too medically technical for us. So for example, there's these like worst analysis, which we really didn't know what that meant. So we had to remove those as well for the purpose of our project.
All right. Okay.
Okay, sounds good.
Thank you.
Okay.